Hi, I'm Gene Rohrbaugh, and today I'm going to introduce you to the computer science topic of searching. Computers store and manipulate data. We store things like numbers and words, music, video, documents, spreadsheets, and we manipulate them by editing the content, playing videos, displaying or printing images, and so on. Anything that a computer does, it does by means of a program. So first, some definitions. An algorithm is a step-by-step procedure for calculating a solution or solving a class of problems. A program is an algorithm implemented in some programming language so that it can be run by a computer. A crude generalization would be that computer scientists focus on developing algorithms, while software developers implement these algorithms as programs. It's not entirely accurate, but it's a start. So some examples. We could write an algorithm to calculate the square root of a number, to convert a color image to black and white, or to find the shortest route between 2 points on a map. We're going to focus, though, on one very common task, searching. The algorithms we talk about here could be applied to any kind of data, searching for occurrences of a word in a file, searching for a file on a disk, searching for students' records in a database, or searching for songs by a particular artist. We'll simplify by using just a list of numbers for our example. But remember that the same process could work for searching any kind of data. So, imagine that we're looking for a particular number in a list of numbers, say the number 41. The first algorithm we'll consider is called linear search, or sometimes sequential search. Linear search works by starting with the first element and considering each in turn, comparing it with the target that we're trying to find. So we start with the first element, 49. Is 49 equal to our target, 41? No? Well, then we'll continue. We move on to the second element, 37. And 37 isn't our target, so we continue. And similarly with the third element, and the fourth, and the fifth, and finally at the fifth we find the value that we're looking for. Remember, this approach isn't just for finding numbers. We could just as easily be searching for songs by Bruno Mars. When we get to Treasure, we find out that this song has an artist of Bruno Mars, and so we stop our search. Now here's an example of how computer scientists are concerned with theory. When we ask the question, how efficient is the linear search algorithm, we could answer it in several different ways. For now, we'll just concern ourselves with the number of steps that it takes to find an element. So, what is the best case scenario? If we're lucky, the item that we're looking for will be in the first position. In that case, it only takes one step to find it. What's the worst case scenario? If we're extremely unlucky, the item that we're looking for will be in the last position. In that case, it will take n steps, where n is the total number of elements that we have. Here, n equals 7. And the average case, assuming that we search for elements with random distribution, is n divided by 2. Again, n here means the total number of elements that we have. Now let's consider an alternative algorithm known as binary search. Notice a key difference before we start. For binary search, the elements are assumed to be in order, and as you'll see, they must be in order for binary search to work. Whereas linear search starts with the first element and considers each in turn, binary search starts with the element in the middle. Compare the target, 42, to the element in the middle, 41, and we see that 82 is greater than 41. Since 82 is greater than 41, we can rule out 41 and everything to its left. Remember, we've assumed that the data is in order, so 82 can't match anything to the left of 41 because everything to the left of 41 is smaller. Notice how with one single comparison, we've ruled out half of the available options, so that now we have only 3 left to consider. And so we repeat the process, comparing our target, 82, with the middle element remaining. And we get lucky this time. We find the target after only 2 comparisons. But even if we hadn't found it this time, at worst, we would have had to make 1 more comparison, a total of 3. So what is the efficiency of binary search? The increase in efficiency over linear search might not be apparent based on the small examples that we've looked at. But the process of eliminating half of the remaining options with each comparison is incredibly powerful. The larger the number of elements we're examining, the greater the savings in efficiency over linear search. The best possible case, just as with linear search, is when the target element just happens to be in the first place that we look. In this case, it's in the middle. In that case, it just takes 1 step. The worst possible case for binary search is determined by calculating how many times the data can be cut in 2. If you've ever studied logarithms in math, the formula is log base 2 n, again where n is the number of elements. Notice how slowly log base 2 n grows compared to n. With 100,000 elements to search, binary search will only take at worst 17 comparisons to find a target, compared with linear search, which could take the entire 100,000 comparisons. Another way to look at it, every time we double the number of elements to be searched, the worst case for linear search doubles, while the worst case for binary search only adds 1 single comparison. So that's it. Linear search and binary search are 2 different algorithms for finding an element in a collection. Linear search is easy to conceptualize and easy to program, but it becomes inefficient for large data sets. Binary search is much more efficient for large data sets, but it requires the data to already be in order.